This is Lab 1 on convergence concepts for contemporary statistical inference. I'm Professor Bloom, and we're going to talk today about convergence of random variables and look at some interesting cases and mainly get used to thinking about the behavior of sums of random variables and scaling them so that they have the behavior that we want them to have. And this is going to be a theme that comes up a couple times or a number of times as we go through class. So convergence concepts. And a good place to start is the law of the iterated logarithm, because in some sense it's an edge case. And I think everyone's used to thinking about, oh, I maybe have a sample mean, right? And what's the sample mean? The sample mean is the sum of the xi's over n. And in the first semester, you learned that this thing converges to its expected value, right? And so essentially what you're doing here is you're taking a sum of random variables, right? Here's your sum of random variables, and you're scaling it. So it's the sum of the xi's, which I'm just going to let be Sn, and then you have 1 over n. So you're scaling it by 1 over n. And if you scale it by the right sequence, this will go to something meaningful, the expected value of x. Well, if I were to scale that by something else, like 1 over n squared, 1 over n cubed, this thing would go to 0 in most cases. So the law of iterated logarithm gives us a particular edge case about how fast sums can grow related to how they converge. So let's talk about that. And so this is a case now where I'm going to go back here, and it's the law of the iterated logarithm. And I have a bunch of random variables, x1 through xn. They all have expected value 0, variance 1, and I'm going to let Sn be their sums, and just so that the Sn I can keep track of. So that really should have been an n up there, so that I can keep track of these i's. And the law, the iterated logarithm says there's this thing called the limit supremum, all right? The limit supremum, I'm just going to use another color here because I got lots of these colors, and colors can be fun. The limit supremum here is equal to the sum divided by the constant. And the constant is square root of n times log n. Well, log n is really slow, so it's just a hair faster than, a hair slower. I think I said it right the first time. It's a hair quicker than root n. And that thing is root 2. So what does this mean? So before we unpack this, I'm going to give you a picture. The first thing we need to think about, what are these supremums and infimum type things? And their formal definitions are down here. But for those of you, just as a quick refresher, if I give you an interval, and that interval, it's the unit interval, goes 0 to 1, and I ask you for the max, well, 1's included in here, so that's the max. And if I ask you what the minimum is, well, that would be 0, because the min's included. Well, what if I give you the open-ended interval and ask you, what's the maximum? Well, there is no maximum, because whatever number you give me, I can always add something to the end and give you a higher number. And there's an infinite number of numbers in there that are larger than the number that you give me and smaller than 1. So 1, though, is not in the set. So in some sense, 1 is an upper bound, but it's the smallest upper bound. And that's effectively what the that's effectively what the supremum is, what this supremum is here, okay? And the limit supremum is the limiting least upper bound. Likewise, for the infimum, that is analogous to the minimum. It is the greatest lower bound. In this case, that would be 0, would be the greatest lower bound. And the limiting infimum would be the large sample greatest lower bound. So I have these definitions here, and you can write them so that you can kind of understand these things. This at least helps me. You can think about, well, okay, what is this? And this is just the definition. And if you think of a sequence, x1 through, say, x what are we going to, xn, and then it goes on for more. What this says is that for any n that you pick, say this n, I can take the maximum or the supremum over this tail piece here. And if I picked a different point in the sequence, if I picked here, I could take the maximum over that or the supremum over that. And in fact, this now you're going to get a sequence of maximums. You get a max here, you get a max here, right? And this is the other color max. You get a max here. So you end up with a sequence of maximums. And so this is the limiting maximum. And actually it's the limiting supremum. All right? And likewise, something similar for the infimum. All right. The interesting thing about the law of the iterated logarithm is that it is effectively in between the law of large numbers and the central limit theorem. Well, so in what sense do you mean that? Well, if you think about the law of large numbers, okay? If you think about the law of large numbers, that is a limit theorem that tells you about the behavior of this guy, right? And the central limit theorem tells you about the behavior of what? Well, the central limit theorem kind of tells you the behavior you might think about of a z-score, right? Of a standardized mean. Sigma over the square root n. And if we had mean 0 and variance 1, you'd end up with root n x bar, right? And root n x bar just turns out to be the square root of n times Sn over n. And these root n's cancel, so it's square root of n over root n. Okay? What we're talking about in this case for the law of the iterated logarithm is the in-between case. So Sn over the square root of n. And I'm going to make this just a little bit bigger by adding log n. So it's in between in that sense. And the law of the iterated logarithm gives you the rate. It gives you the rate at which, right? It's the scaling sequence at which this sequence will converge in probability, but not almost surely. Okay, and I'm going to give you some examples about how that works in a second. But first, I want to talk a little bit about give you some examples of the limiting supremum and infimums. So here I have a nice function. The function's in black, and it's this weird isolating function. And you can see it's going up and down, and up and down, and up and down, and up and down, and up and down. And I just picked this function so that it would be easy to sort of illustrate to you what the maximums and minimums, or the greatest upper bounds over a period, over the x space would be. And so if I wanted to know what's the maximum of this function over the entire x-axis here, I would just take the maximum. So it would be, well, this would be right here is a good potential. This is a max, this is a max, this is a max. And then I take the maximum of all those maximums, okay? If I take the maximum of all those maximums, I'm going to get this guy out here, which is the supremum. The limit supremum. So essentially what you're doing is at any particular point, and let me use a different picture, you're basically breaking the graph in half and you're saying, give me the maximum and then give me the minimum. And then you take this line and you move it back and forth. And that's the maximum is that blue line that I have there, which is the supremum of the function when x is bigger than the point at which you're looking. And the red is the minimum or the infimum of the function, basically to the right. Okay? And so what you can see is that the maximums are going down over time, right? And they're converging. They're converging to this dotted line right here. Okay? This is the limit supremum. And here you can see the infimums are getting bigger, right? This is the max over everything here. This is the max over everything this way. And these are growing just ever so slightly, and so this is the limit infimum. Okay? And when a function converges, when an ordinary function converges in a proper way, the limit supremum turns out to be equal to the limit infimum. Right? So these two things come together and pinch together at some particular point, and then that's the limit. But in this case, this function oscillates, and it gets to a point where it actually has an element of oscillation that doesn't go away. And so the limit supremum and limit infimum of this function don't come together. And so this is an example of a function that will oscillate forever between two limits. And so this function is not going to converge to a point. It will always be within this interval right here, but it's not going to converge to a particular point. All right? And so what the law of the iterated logarithm says is that the limiting supremum has a bound. Can't get too big. These maximums can't be too big. All right, let me just read what I have here. So we talked about this. What does it mean for the sequence when the limit supremum and the limit infimum are equal? Well, we know this now. This means that in the limit exists in a loose sense. It exists, and then knowing this behavior is very helpful for understanding our function. And so the law of the iterated logarithm, if we go back, it says the limit supremum here of Sn over n of this sequence, okay, is going to be root 2. And I'm going to illustrate this. We'll illustrate this with some simulations as we go through when I get done with this in a minute here. Okay? All right. So this is all about scaling sums and their behavior and what's going on. All right. Let's talk about the connection here with the central limit theorem and the law of large numbers. So I'm going to take the sequence of sums Sn, and I'm going to multiply it by 1 over the square root of n. So we know this as Sn over the square root of n here. And I can multiply this guy by root n over root n, so that the bottom is n and Sn over n is x bar. And then I get a root n out here, right? So this is the same as this. Okay? And I know where this converges in this case because it has mean 0 and variance 1. So this converges to a normal distribution. Well, what does it mean for this sequence to converge to a distribution? What it means is that the sequence doesn't end up at a particular point. So if you were to follow a particular sequence out to infinity, it'll end up around 0. Most likely, most of the time, it'll be, almost 100% of the time, it'll be within, say, 3 or 3.5 standard deviations of 0 is where it will settle down. But it doesn't have to settle down exactly at 0. All right? And so what the central limit theorem implies is that the scaled sequence does not converge to any particular point. Okay? So one way to think about this is we can imagine, okay, I'm going to draw a sequence. Here it goes, and here it ends. And I'm going to draw another sequence, and here it goes. I'm going to draw another sequence, and here it goes. Here's another sequence, and another sequence, another sequence, another sequence, another sequence. And you just keep drawing. What the central limit theorem says is if you look at the distribution of ending points, okay, that this thing is going to be roughly normal. That's supposed to be a normal distribution. Right there. Okay? So you'll get these sequences that come out of here. Now, and so this doesn't converge to any point. It doesn't converge in probability, and it doesn't converge almost surely. So it does not converge in probability and does not converge almost surely to any point. So now, in contrast, what does the weak law and the strong law of large numbers say? All right. Well, they say basically the same thing, but under some different conditions. And they said, well, if you take a look at this Sn, the sequence of Sn, okay, and then you scale it by n, what's going to happen is it's going to go to a point. Let's make that point 0. Or 0. And then here, you'll start off 0. And all of these paths are random, but they're all going to end up at around the same place, right at 0. Okay, and that's what the strong law of large numbers does. So by adding that extra root n on the bottom, you're essentially compressing these edges right down together right here at this point. And what the law of the iterated logarithm says is it's between these 2 points, because what happens is if you take Sn and you divide by root n and then this extra little part here, this sequence will converge to 0 like this over here, okay? But it only converges to 0 in probability, not almost surely, okay? And so now we have to remember, well, what's the difference, right? Convergence almost surely is a stronger condition than convergence in probability. Because what convergence almost surely means is you reach a point, and after that point, you are always very close to your target. You don't leave a particular neighborhood of that target. So you may be within 10 units after some particular point, or 4 units at that particular point. And in fact, for any neighborhood size, you can pick a point for which you will never be beyond that size away from your target point. So what this means, okay, is that in fact this sequence will be less than epsilon, because remember our target point is 0, so we'll be within epsilon, okay, with probability that approaches 1. So we can write this as this. So the probability that this sequence is bigger than epsilon, so you're further away from your target than epsilon, converges to 0 as n goes to infinity. But this is convergence in probability, which means it doesn't happen 100% of the time. It may happen a very, very, very high percent of the time, but there's a small percentage of time at which you're going to get some random points that are way outside of epsilon, okay? And this sequence doesn't converge almost surely. So it will drop out of the interval 0 here infinitely often, all right? And in fact, what the law of the iterated logarithm says, it visits points in the interval between 0 and root 2 almost surely. And so you're always going to get some random things that show up between 0 and root 2, all the way up to root 2, even a small amount of the time, probably not even enough time to simulate and see. All right. So we'll just do this. I'll come back to this too, but before I illustrate, these are the definitions of here again, convergence and probability and convergence almost surely. So convergence and probability means the limit that the probability that your sequence is near your target or is further away from your target is greater than epsilon, okay? That probability goes to 0, right? The limit of that probability goes to 0. Whereas almost surely the limit's, of course, inside the probability, but that means the probability that you end up exactly at your target is 1. So one way to think about this is that for almost sure convergence, and this is important, a simplification of this idea is that you can always find a point, okay, capital N, such that for any sample size larger than that capital N, you're equal to the point W. So that is, after point N, the sequence is always equal to W. So let's say this is capital N, this is W, and then this is the sequence Wn. If the simplification is this, so that you have a sequence after here, and then after here, and then it's always exactly equal to W, okay? Now in real life, You can't have this in real life because for any sample size, there's going to be a little variability, a little stochastic nature. And so what convergence in almost surely says is, okay, well, since I know I can't equal W exactly, what I'll say is that there's always going to be a neighborhood here, and the width in this neighborhood is epsilon and minus epsilon, for which after n you'll always bounce around within that neighborhood. You'll always be within epsilon units of the truth. That's what convergence almost surely means. Convergence in probability, on the other hand, means very often, you're going to get close. But you may get close and then pop out for a second and then come back. Okay? Because all you're doing is the chances of being close are getting really, really, really high. But when you're not close, you can be not close by a lot. And that is what's going on with convergence and probability. And so one way to write this back to our supremums is that convergence almost surely, you can think about another definition is it's the limiting probability of the supremum of the sequence here being far away. And what I like about this particular definition is that it is parallel to this definition up here. It's the limiting probability that the sequence here is bigger than epsilon away from 0. That Wn is more than epsilon away from W. Well, this is the limiting probability that the sequence here is more than delta away, right? I could have just used epsilon here to make life a little bit easier. It's more than epsilon away. Except what this says is this is the supremum, so this is the maximum of the tail. I'm cutting off parts here. And what I'm saying is the max over, say, this part here, okay, is bounded, is never going to be bigger than epsilon. So I know I'm never far enough away. And the limiting probability will be 0. So that's the connection, is that here you have some control, here down here, you have some control over the maximum distance that you'll be away from W. Here, you might miss W, and by here, I'm back up here now for convergence and probability. You might miss W, but you can miss W by being very far away. Down here, when you miss W, you can't be more than epsilon away because the maximum is controlled. All right? So that's basically the idea. All right. Let me put that back there. Okay. So let me scroll up here. And what do I have written? I said, so this is written in this particular way. And for convergence and probability, no such point exists. And this is exactly what I talked about, that the probability that the sequence Wn is near W shrinks to 0, but there's always a non-zero probability that the sequence will leave a close neighborhood of W. This probability, of course, does not go to 0. Convergence almost surely is a stronger mode of convergence because it means that there is a point after which the sequence is always within that tight neighborhood of the truth. So this is a good example and good to think about. I think that these are tough concepts and they require a little bit of thinking. And so one thing that helps is to actually do some simulations, which I will show you in the next video about what exactly is going on. But one of the things that I can't simulate, one of the things that interests, I can't simulate having things randomly come in and out of this interval just because I simply can't run enough simulations to have that happen frequently enough, right? This happens 1 in 1 million times, 1 in 10 million times, and if you get out far enough. And so I'm going to illustrate the convergence behavior, but I won't be able to illustrate sort of edge cases where you have some sequences that are always within the neighborhood and some sequences where they jump out every now and then. And we will go to that. We're going to go to that next.